Imagine trying to hear a whispered secret at a rock concert. The raw sound is there, but the overwhelming noise makes it impossible to understand. In the world of electrical engineering, sensor data often faces a similar challenge. Signal conditioning is crucial for sensor data integrity because it transforms raw, often weak or noisy, sensor outputs into a clean, standardized electrical signal that can be reliably processed and interpreted by analog to digital converters and microcontrollers. Without it, your data would be inaccurate, misleading, and ultimately useless. The necessity arises from several fundamental issues inherent to sensor operation and environmental factors. First, many sensors produce very small electrical signals, often in the millivolt or microvolt range, which are easily obscured by electrical noise. This low amplitude requires amplification to bring the signal within a usable voltage range for subsequent processing. Second, sensors are susceptible to electromagnetic interference, power line hum, and thermal noise, all of which distort the true measurement. Filtering is then essential to remove these unwanted frequency components, isolating the actual data signal. Additionally, sensor outputs can exhibit nonlinearity or a direct current offset, meaning their response isn't perfectly proportional to the physical quantity being measured, or they have an inherent baseline error. Signal conditioning circuits correct these deviations, linearizing the response and removing offsets to ensure precise measurement. Practically, this means carefully selecting and implementing various electronic stages. An instrumentation amplifier, for example, provides high common mode rejection, effectively amplifying only the differential signal while ignoring common mode noise picked up equally by both input lines. Low pass, high pass, or band-pass filters are then employed to attenuate noise outside the signal's frequency range. Furthermore, offset correction circuits can be used to shift the signal's baseline, and linearization techniques, often involving lookup tables or specialized analog circuits, adjust the sensor's nonlinear response. These components work in concert to prepare the signal for the analog to digital conversion process, ensuring that the digital representation accurately reflects the physical phenomenon. One critical insider detail is the importance of anti-aliasing filters when digitizing signals. These are specialized low-pass filters placed before the analog to digital converter to prevent a phenomenon called aliasing, where high-frequency components in the original signal appear as lower frequencies in the digitized signal, leading to irreversible data corruption. Another is impedance matching, ensuring that the sensor's output impedance is compatible with the input impedance of the conditioning circuit to maximize power transfer and minimize signal reflection, a crucial aspect often overlooked by beginners. By meticulously applying signal conditioning techniques, engineers ensure that the journey from physical phenomenon to digital data is smooth and precise. This meticulous preparation safeguards the integrity of every data point, enabling accurate analysis, reliable control system operation, and robust decision-making based on trustworthy sensor readings, ultimately foundational to the success of any embedded system.